Okay, so last time we talked briefly about the idea of a computer, okay? That computer is an engineering process, hardware-wise, and that in the IB program we're not going to look specifically at specific little details of that, but as an overall generality with it. We talked about how it's essentially just a state of on or off, positive, negative, 0, 1, lights on, lights off. We talked about how data is represented. So data itself could be represented as a 0 or a 1 or an on or an off, or numbers more complex than that, or letters. Different ways data will be represented, and we'll be talking about that in this unit. We talked about the architecture. Should we reduce how many instructions we give the computer or give it complex sets of instructions? We talked about all that, and we talked about how essentially a computer is just a two-state system, and everything is built from that. So, here's what the IB curriculum actually says you need to know about this. First point, outline the architecture of the central processing unit, the CPU, and the functions of the arithmetic logic unit, the ALU, and the control unit, the CU, and the registers within the CPU. So there's some terms here you're going to learn. CPU, ALU, CU, and registers. What do all those things mean from an architecture standpoint? It says here, students should be able to reproduce a diagram showing the relationship between the two, including memory address registers, memory data registers, etc. Explain the machine instruction cycle. This should include the role of data in that cycle. Explain the main functions of an operating system. Outline the range of application software. Those last two I think are pretty easy, but we'll move through there. So let's talk basics. I'm going to go quickly through this because we've already talked about it. A computer is essentially a collection of switches. Those switches, in reality, are little transistors etched into a piece of silicon material. So if you've ever heard of Silicon Valley, that's because silicon is the primary element used in the creation of transistors. But again, if you imagine things as just a series of light bulbs connected to a series of light switches that flip the switches on and off, certain combination of switches can make certain lights create certain letters. If you have master switches that flick certain switches, you are essentially using one switch to flick multiple switches, and then what you essentially have is the monitor of the light bulbs, RAM is the switches, and the keyboard is the master switches. That what essentially is what a computer would be consistent of. Okay? We represent on-off positions as 0 and 1 in the binary code system. Okay? If you keep in mind that we can do adding to do any kind of math, and we talked about that last time, because subtraction is just adding a negative, multiplication is just repeated addition, and division is essentially just repeated subtraction. To the computer, everything is just adding, and the only two numbers it needs to add are 0 and 1. Okay? So if we can find a way to represent everything else as just 0 and 1, and just do adding, we can make a computer. It's coding that makes that happen. It's the logic behind that. Okay? The first computers were switches based on something, well, actually, even before vacuum tubes, they were actually magnetic switches, just like the switch on the wall here. And magnets would switch them on and switch them off. That's how they do it. But these were huge and clunky and mechanical. Then they moved to vacuum tubes to indicate on and off. Those were less clunky, but they heated up and they would burn out. Okay? So what engineers did was they started to make these more efficient, faster, smaller, use less electricity. And the transistor and the silicon was kind of how that worked. So now, because we can make them smaller and we can have many more switches working way faster and using less electricity, we can build smaller electronics that still do the logic we need it to do. The logic for this is based on something called Boolean logic, and we're going to look at that in this unit. And you guys know what a Boolean is. It's a state of on and off. So we're going to build a whole mathematical system based on on-off. We're not going to use the traditional math symbols you're used to. So you're used to in math combining numbers with adding, subtracting, multiplying, dividing. Instead, you're going to use these three math operations, and, or, and not, which you've seen in coding, but they're actually going to be the things we use in math instead of adding, subtracting, multiplying, dividing, because we're dealing with a two-state system. Okay, and that will represent addition. So what a transistor essentially is different kinds of silicon. Okay, there's silicon dioxide, and then there's something called p-type silicon, and then there's polysilicon and n-type silicon. This is at a very microscopic level. But basically, the way the silicon works is some silicon acts as a conductor and some acts as an insulator. So essentially, if you have something coming in this way, imagine this is where electrons can come in, and this is where electrons can come out, it would be in a state of on as if the electrons are flowing through. That's on. And it would be a state of off if the electrons aren't flowing. Make a simple switch. That's what it is. On and off. Okay? The way we can do this is just by dealing with the electrons. So electrons, negatives, what are they going to want to do to other negative electrons? They're going to repel each other, right? What are the negative electrons going to do when they encounter positive? They're going to attract each other, right? So if we push some positives down here, the negatives will get drawn in by the positives, and then they can flow out that way. So that causes that. If we push negatives down there, it essentially pushes them back and switches. So basically by changing the electron flow, we can switch them on and off. And we don't need a lot of electricity to do that. We need very, very little. So in the next few slides, I kind of explain that. If we give a small positive charge to the transistor, it spreads into the layer of conductive polysilicon, and it embeds into the non-conductive polysilicon, and that positive charge attracts the negative electrons from the source out through the drain. So it causes, by pushing the positives down there, it causes it to start pulling electrons through to cause an on state. Okay? Creates that electron vacuum down there, and the electrons flow in and flow out through the drain, representing an on state, or we could just call it a 1. If I switch this to a negative charge, then it essentially turns it off. So just by applying a positive or negative charge, I can set this piece of transistor into an on or off state. It's very simple. It's not, I mean, this is a kind of a complex diagram, but the actual process is super simple. And remember, this is happening at a very small microscopic level. So from that transistor, we can build a microprocessor. What a microprocessor is everything it needs to do the logic we need it to do. Microprocessors are what build your CPU. CPU stands for Central Processing Unit. It's the main brain of your computer. It's the chip you pay for when you buy a computer. It's what all the money is really based around. All other components, from RAM to disk drive to monitors to keyboards to cases for your phone, serve to bridge a gap between what you want to do and what the microprocessors, CPUs, are going to do for you. Now, if we go back in time, even not quite as back as the one in the back corner there. Actually, no, sorry, that is the one. That computer is called an Intel 8088 computer, back there. Okay, and that's why I have it there. That one wasn't made by IBM, but nonetheless. Generations that followed included the 80286, the 80386, so notice they're just upping the number there, the 486. 486s was the most popular brand of microprocessor ever made because they held the longest production line. They were in production the longest. And this is in the 90s. You ask your parents, they probably remember buying a 486 computer. From there, they then started using names to describe it. And the first name that even your parents might remember, and maybe you guys are old enough to remember, was one called the Pentium class computer. Oh, I'm seeing a few nods, so some of you have heard of this before. Then they ended up making a Pentium 2 class, right? Okay, so these generations were based on two criteria. How fast can that thing work, and how much data can it handle at once? Okay, we talked about that. Should I give it complex sets of instructions, or should I give it simple sets? This is what the engineers would build, okay? So when they moved into Pentium class, and there was a Pentium 3, etc., okay? We now want to talk about something called the ALU, which was the arithmetic logic unit. So built into your CPU is something that just does math. That's what the arithmetic means, right? So it basically is part of the CPU to just do math. The ALU, as you can see, does that math, and that was the Pentium that separated it as well and said, well, how about we have one ALU that does math on integers, because I don't have to worry about, remainders and all that stuff. And then I'll have another ALU that deals with double and float values. And if I can separate those, I bet you that'll work better. And it did, right? That was a good idea. Then they started saying, how much bits of data can we handle at once? Can we handle 16 bits of data? How about 32 bits of data? How about 64 bits of data? Okay. Why not, right? Well, you can be the engineer that does that, right? But then they also said, what about storage on the chip? Okay, so hang on, let's put this into a diagram state here for a second. Okay? So we know that the whole thing is called the CPU. Okay? It handles all the processing. It's the central processing unit. But somewhere within this is the ALU. And what does that stand for? Who remembers? Logic unit, yeah. So it's the logic for doing arithmetic. They also separated that into a section that handles whole numbers and decimal numbers. We might call that, instead of that, we might call those integers and floating numbers, or doubles. Okay? It separated it into those two sections. Okay? But we still need more. Think of that as just like a little calculator in there that can do lots and lots of math really fast. But there's also one other part of the CPU. Okay? I'm guessing you know what the U stands for, based on the other ones. Central processing unit, arithmetic and logic unit. Not central, no. Good guess. Okay, if you think back to grade 10, just a sec, I'm going to give you a hint. Listen for the hint. If you think all the way back to grade 10, I said computers are basically composed of two main functions. Remembering stuff and the other one. You said it. Control unit. This is the control unit. Because it still needs to take that data and figure out what I'm doing with it. So it's like, well, yeah, I can let you do the math. The control unit says, here, do this math, because it figured out that that's what it needed to do. It's in control. So a CPU consists of the ALU and the CU. Okay? Let's back up the bus here a little bit. All the way back to the IB document. Outline the architecture of the central processing unit and the functions of the arithmetic logic unit and the control unit. Okay, so you can see I'm matching up with the curriculum there a little bit, right? So that's the idea, right? I'm covering that content as we move forward. Okay, we're going to go further than that, though. Whoops. Okay. So the microprocessor follows the instructions of the software to do this stuff. So with its two main units, the ALU and the CU, these components are connected through what you might call wires, but they're essentially electronic pathways, and the term that's generally used in the hardware is that they are bused together. So you're going to hear the word bus to describe the connection between them, right? So sure, this is the ALU. Group it together. And this is the CU. And when data flows between them, okay, we call that connection a bus. Now, we're going to get more specific about that, but that's the case. Now, the CPU is going to be connected to other parts of your computer, obviously, including memory. That will also be described as a bus. Basically, any type of, and I'm going to put this in air quotes, wiring that connects parts of your computer, we tend to use the term bus, okay? All right. A data bus moves data in both directions, okay? By the control bus, or now, okay, so now they're specifying how that works. An address bus sends addresses from one component to the other. The CU tells the rest of the system how to carry out the instructions. Signals between the ALU and main memory are bused between each other. Direct electronic signals from main memory to your input-output devices, like your keyboard, are bused. And commands go all over. So as you know, the computer is sending electricity out all over the place. The ALU performs the arithmetic and also does logical comparisons. We'll talk about that. And essentially controls the speed of that operation. Okay, so here's a diagram. 1, data comes out of RAM, we'll talk about RAM later, from secondary storage into RAM. So let's say this is a piece of your code. A piece of your code is moved into the computer's RAM memory. 2, data is then bused from RAM into the ALU. And in the ALU, it has memory built into it. Memory are what registers are. Registers are just pieces of memory. So when you buy a computer or piece of hardware, that chip has memory in it. More expensive chips have more memory in it. Often that's what you're paying for. When you look at two chips that seem to have the same speed, but this one's more expensive, I mean, it could be because the company's charging more, but generally that's because it has what's called more onboard memory. Sometimes a general word for that is cache memory, C-A-C-H-E, okay? So anyways, the data is bused up to the ALU. The CU tells the ALU what it needs to do with that data. It says, hey, add these numbers for me, okay? The ALU does it. Like it's just a workhorse, this thing. It just goes, sure, we'll do it. Doesn't think at all. The CU does the thinking. It says, do that for you. I'll add those things together. Generates an answer. The answer is sent back to RAM saying, here you go, here's your answer. And then that could then be bussed along to, say, your monitor to show you the answer of your equation, right? So the CPU contains printed circuit boards with thousands of transistors, those little switches, with the silicon on it to create the system that does all this as part of what's called the system board. Now, when I say board, what do you guys think of? Other than the state you're in right now as you listen to me. Okay? A board game? A wooden plank? Sure. But the word board in this context essentially means the component where all the circuitry's on. Okay? So if you've ever opened a computer, you probably have seen these things. Okay? I have some down here. I keep old ones. Okay? Okay, so you see this? If I was to ask you what this was, you may not have used the word board to describe it. Okay? But that's often the way it's described. And I heard someone say the term motherboard. That's a common term. Would you say this is a motherboard? Why not? It's too small. Could be, but it could be from an old thing. But then what would this be? What would be another word that uses the word board in there? Circuit board is general. But when you buy a computer, what else can you do? Can you pull some of these out and put other ones in? Okay. Have you ever heard the term soundboard? Or video? Wait a minute. Do we use the word video board? What do you say? Card. Okay, so here's the thing. Card and board can be interchanged. This is also the mother card, the sound card. Okay? But you can also call it the video board. But there's a general term for boards that plug into the motherboard. They support it. A sound card supports the motherboard. A video board supports the motherboard. Why? What's so important about the motherboard? What's sitting on the motherboard that makes it important? The CPU. So that's the main brain. The motherboard's in charge. All of these can also be called, the term we use, daughter boards. I so wish Emily was here today. This is the most pro-feminist display today. So the terms are used are feminine terms. That daughter boards plug into the motherboard. Okay? And I don't mean they necessarily plug in directly, They are bused together. Okay? So these are words you can start getting used to. Board, card, etc. Okay? Motherboard, daughter board. Okay? System board. I'm so bored. You get the idea. Okay? All right. So let's talk about the history of its development. We talked a little bit about this before. So it was this difference between a complex instruction set and a reduced instruction set that engineers still to this day debate in a lot of ways. Complex instruction sets is the design to handle a large number of instructions at once. But that reduces the speed. But if it's doing 20 instructions at once, maybe that's okay, because although the risk is faster because it doesn't handle as much, it can only do one at a time. This one can do 20 at a time. That's a pretty good debate, right? If you can get somebody who can do one thing at a time but really fast, and you can get a different person who can do 20 things at a time but he's slower, which of the two do you pick? And that was what I gave you guys as a thought experiment. And it's not an easy answer. To answer it, you really have to test out which of the two is going to work better. And so that debate rages on, which is the better system. Pre-1970s, it was all about RISC architecture. Because really they didn't have the engineering to build CISC architecture. But since the 1970s up to 2000, then they started bringing in CISC architecture. Okay? Because now actually coding could catch up as well. So now coding could match up with CISC architecture. Okay? You guys have probably grown up in this experience where now you can have dual processor systems. How do you write code for that? How do you write code for things that can do two things at once? Or do you just not worry about that as a programmer? One of you asked me the other day about something called multi-threading in programming. Well, that's what that is. Different threads can be assigned to different parts of stuff. It depends how far the programming language can go to get up to match up to the hardware. But around the 1980s, the debate changed a little bit. So although CISC architecture hit up to about the 2000s, in the 1980s, they said, you know what, let's revisit the RISC architecture. I wonder if I can build a computer that's actually faster with a RISC architecture. And the debate rages on. Okay? It also has to match up with our programming languages. Since the 1970s, more and more programming languages try to match up with the hardware. Okay? So is Java a good fit to this? Is C#? What about C++? Also, what about memory? In the 1970s, memory was super expensive. So they tried to make hardware that match up so to try and reduce the amount of memory. Now, memory is super cheap by comparison. Okay? So now that we have more memory, all of this starts getting, it's not a simple question, which way do I go, because there's so many dependent variables here. Okay, what designers found was, though, that they could make CISC architecture, but it was rarely being used that way, especially by the coders. And I bet you guys wouldn't think, and when you write code, you don't think, well, I'm going to write this piece of code to work on that processor, and this piece of code is going to work on that processor. It ends up becoming too hard of a problem to solve in that way. So they thought, you know what, if the coders aren't writing instructions to be used this way, why are we building architecture this way? And that kind of pushed why RISC architecture tends to be more popular in that sort of engineering field. Okay? The architecture developed to match up with what the programmers were building. Okay. A little more detail. So now let's increase this diagram out to here. So we have our ALU and our CU, arithmetic logic unit, control unit. Data is being bused back and forth. So over here, this is memory, but let's get a little more specific about what we can call it. We can call it the immediate access storage of memory. In other words, this is memory that you can get at immediately. So when you need memory, I'm right here for you. That's like having stuff in your pocket when you need it. I got it right here. Oh, wait, my pocket's full. I have to go over here to my backpack to get the next thing. Well, that little travel I just took over to the backpack took a little bit of time, and time is valuable to the computer. So the more we can have at immediate access, the better on the CPU. Okay? This is essentially RAM, ROM, and other types of storage. We'll talk about the difference, okay? And what's called cache memory. So in the CPU, as part of our diagram, we have to include some amount of memory in this diagram. So if I go back to here, we also need to include memory. Okay? Let's use the term IAS again. Immediate Access Store or storage. And our busing also has to include this. So we're also busing data into the memory. This is on board the CPU. Notice that. So we have ALU, CU, and a memory in the form of an IAS. Okay? So, just to refresh your memory. Oops. Ah. Man. Let's try that again. There we go. Here's that first point from the IB again. Outline the architecture of the CPU with the functions of the ALU, the CU, and registers within the CPU. Registers, okay? Over here it says the memory address registers and the data registers, the MDR and the MAR. So we're going to go even deeper into these acronyms a little bit. But again, notice what the IB says is your statement of assessment. And these are just what they call teacher notes, which means this isn't necessarily part of the curriculum over there. So right now, you guys should know what an ALU is, a CPU, and what registers are. That's the basic curriculum point. Does anyone not know what those three things are? Let's go 4 things. CPU, ALU, CU, register. You could right now, during an exam, write down a definition of them. Could you reproduce that diagram? Okay, that's something to think about. Okay, could you do that is an important thing. I mean, I'm just mentioning it now, right? All right. A register is memory. Okay, think of it as you're registering, you're recording whether it's on or off. Register means memory. Okay, so the function of the CPU, data is exchanged between these units using buses. Okay, data moves in a bus in both directions, back and forth, being set by the control unit. So there's a control bus. There's an address bus because each register has an address. Think of it like you guys are mailmen and you have to deliver a letter. You need an address on that letter to deliver it to the right house. Well, you will take a bus to get to that house. That's the address bus. It's taking you to the right address. That house is a register, right? It's basically registering on or off. Okay? The ALU is doing all the math. It's doing the calculations, which actually what we know is it's just doing adding. And it's the control unit that figures out what the instructions are to send them to the other units to do the operations. Okay, I think we can get a little bit through this and then we'll call it a day today. Okay, let's go deeper. Okay, within the control units are 2 important registers: the current instruction register and the sequence control register. Okay? These are not, as you saw, part of the IB curriculum per se, but there is memory on the CU, and there's even stuff on the ALU, an accumulator. The IAS, also still here. Okay? So I can get into more and more detail if you'd like, but I think at this point, this would be a good place to just sort of gloss over this material. And then next week, let's finalize it. Let's use a little play where you guys will play out parts of the CPU. That'll be fun. I'll get you guys to do that. All right. So registers are an important part because they memorize the on-off switches. Additional registers are all over the place. For example, there's one called an interrupt register, which is used to store vital information that might cause the CPU to pause what it's doing and get its attention. A register, here's the answer to your question, is a small amount of computer memory that can hold a piece of data. So what I don't want you to think is a register is just on-off. A register might hold a series of on-off switches. What that's generally described as one word of data. Now, depending on the system, that could be 16 bits of data, or 32 bits of data, or 64 bits of data, or what's the next one up? 128 bits of data, right? So a register depends on the system how much one piece of data would be, okay? And that's, by the way, how it's connected to your programming languages. That's why, for example, an integer maxes out at a certain value because it's connected to the register values, Okay? Buses are the wiring that connects it. Okay? So they link the microprocessor to memory. They link pieces within the microprocessor. There's buses of different names to do this stuff and move the data around. Okay? So there's a control bus which shows the data, which way it's moving from, which to store. The accumulator stores data. There's this microprocessor. Microprocessors are often use a speed metric on them. They rarely have the memory metric on them, but they do if you look deeper. Some microprocessors will have a memory metric on it to tell you how much memory it has built into it, but mostly they're measured by speed. That speed is in hertz. Do you know what hertz is as a unit? Okay, megahertz, kilohertz, gigahertz. Okay, hertz is essentially how many instructions it can carry out in a second. Okay, so when we're saying 500 megahertz, what are we talking about there? Yeah, lots of instructions in a second. Okay, all right, we'll stop there today. Just a sec.